So we're going to start off this chapter by learning about how to calculate formula mass. So formula mass has to do with the mass of a compound, whether it be ionic or molecular. And the way that we do it is we are going to take the formula of whatever compound that we're looking at, and then you kind of dissect it and you look at the superscripts. So in this case, this compound is CHCl3. So let me go ahead and write it down. So I'll give you a formula, and then it's up to you to calculate the mass. So we have 1 carbon, 1 hydrogen, 3 chlorines. You take the mass from the periodic table. So all of these masses come from the periodic table. And then you just multiply it against however many there are. You add up the entire mass, and that's your formula mass. So just to show you another example, here we have CH2Cl2. So it's slightly different from the one above. But overall, when we add up the mass, we get 84.116 AMU. So here I am going to show you another example. This is in particular a molecular compound, and actually this is caffeine. So if you ever wanted to know the mass of caffeine, here it is. So again, same thing where we take the number, essentially the superscript. That's where we're getting this number from, and then you multiply against the mass of this element. So for example, carbon. From the periodic table, you get a subtotal. So these are your little subtotals, and then you add up to get a grand total. So again, another example, this is specifically an ionic compound hydrate. So what is different about this type of compound is that you have some waters attached to it. And all that I want you to really necessarily learn that's different about this compound compared to the other ones is that you have a coefficient right there. So that right there is called a coefficient. And that coefficient applies to all of the atoms after it. So to break this down, we can write down there's 12 H's and 6 O's. So that's where this 6 and that 12 is coming from. And the reason that you have 12 hydrogens is because you have this 2 right here. And essentially, if you wanted to, you could draw out 6 separate little water molecules, and you would see that in each water molecule there's 2 hydrogens. So if I have a total of 6 water molecules, that's going to be 12 hydrogens total. And then again, we get that grand total, and there's your mass for that compound. So in this chapter, you are going to learn about something called the mole. Now, at this point in time is when I notice students, they start freaking out about this class, because the mole can just be something that's kind of hard to wrap your head around. But if we start off this way, by telling yourself and repeating to yourself, the mole is like a dozen, you will be completely fine. And the reason that I want you to tell yourself this is because that's honestly what it is, except the chemistry version. So like a dozen equals 12 things, the mole will equal a certain number that we're going to talk about right now. So the whole reason that learning about moles is even important is because in chemistry, it's not only important the types of atoms or ions that a compound can have. So we learned about how certain atoms, wherever they are in the periodic table, that will determine their properties. Not only is that important for determining properties, but also amounts, so quantities. So think about H2O2 and H2O. H2O2 is hydrogen peroxide, and H2O, is water. One of them, if you drink enough amount of it, you will probably either something will happen in your body, like some sort of failure, organ failure, or you can die. And then water obviously is it's like the basis of life. So even though they're so similar, in terms of their formula, they're just off by 1 oxygen, right? They are very different. And so I think this is a good example to display to you how quantity can affect properties as well. So in terms of what a mole quantitatively is, the way that you can think of it is scientists took 12 grams of pure carbon-12. Carbon-12 is one of the isotopes of carbon, and actually it's the most stable one. So they took 12 grams of that. They figured out how many atoms were in there, and then they said, okay, that's a mole. So this number specifically, which I'm going to describe a little bit more about in a second, but this number is what a mole is equal to. So the same way that 1 dozen is equal to 12, 1 mole is equal to 6.022 times 10 to the 23rd. And we use this number because it just makes it easier to quantify atoms, molecules, ions. These things are so tiny that, like, even if you had just a gram of one of either atoms or molecules or whatever it is, like 1 gram would contain very many of them. So in order to make it into a number that's easier for us to use, that's why we use moles. So Avogadro's number is a number that we just talked about. Now, he basically established experiments that kind of like set the precedence for scientists later on to actually figure out the number, but he proposed that a volume of a gas is proportional to the number of atoms or molecules in a certain volume, and within that certain volume you will always have the same number of atoms or molecules. You'll learn about this more when we get to the chapter about gases. And then later on, some other scientists who named John Perrin, he won a Nobel Prize for this work, but he actually discovered this constant, which was Avogadro's number, and then he decided to name it after Avogadro since he had done so much work for it. Okay, so now let me tie it together since I talked about this number, but I want to talk about how the name is Avogadro's number. So instead of remember, scientists are lazy. Instead of sitting there and saying 6.02214 times 10 to the 23rd, we would just say Avogadro's number. So just know that anytime I say Avogadro's number, this is the number I mean. Specifically for this class, we can shorten it. We can just use 6.022 times 10 to the 23rd, and you can use it that way. And just finalizing, like connecting the mole and Avogadro's number for us. Remember, think about that mantra about the dozen. A chemist's dozen is equivalent to the mole. So in 1 dozen, there's 12 things. In 1 mole, there's 6.022 times 10 to the 23rd things. It can be atoms, molecules, formula units, particles, whatever it is. And then also remember that you can use it as a conversion factor. So remember how we have our unit equations and we can set them up as however we need to in the fraction in order to convert something in dimensional analysis. We can do the same thing with Avogadro's number. So here in the slide you can see that they set it up this way and then the other way around. So again, think of Avogadro's number as converting really big numbers into numbers that we can understand more. The same way that we use scientific notation to make like really big, like clunky, they're just hard to write, very big numbers or very small numbers. We convert them to scientific notation to make them easier to work with. So if we had 1 mole of gold, then that means that we would have 6.022 times 10 to the 23rd atoms of gold. So 1 mole of anything is Avogadro's number of it. And to help you visualize how big this number is and why it's so useful, if you had 1 mole of M&Ms, how much area would they cover, like on the world? So it could either cover the contiguous US, so the 48 states that are like together, 52 miles deep, or the entire world 1 mile deep. M&Ms. Imagine that. That's how many, if you had a mole of them, that's how much it would cover. So again, just something visual to help you understand the mole and Avogadro's number. So if you had all of these elements, you had samples of them, right? All of these samples here are actually equal to 1 mole. So in each of these samples, they're all different, right? Zinc, carbon, magnesium, copper, whatever, silicon, lead. They're all different, but they all are displaying 1 mole of them. Now, I want you to pay attention to this mass. and see how it's different. We're going to talk about that in a second. So we're going to start building this map. We call it the mole map. And the mole is going to be at the center of everything, so don't forget that. But we're starting off with being able to go from number of atoms, molecules, ions, whatever it is, to moles and back. And remember that we can use Avogadro's number as a conversion factor. So we're going to start off these examples by converting from moles to atoms and atoms to moles. On this first example, we are given the number of atoms of krypton, and then we're asked to calculate moles. So our known, and I'm just going to be lazy here and just label it, our known is this number, and then our unknown is the moles of krypton, right? So we're starting off right here, and we need to go that way. So we're going to set up our known at the front. Atoms. Please get into the habit of labeling everything. I know it's a pain in the butt to write out atoms and then krypton, but it's not going to fly. And you'll see later on for chapter 4 why I don't let it fly, because you can get confused and then things will just start going wrong. And I don't want that to happen to you, like getting a wrong calculation just because you like look back at your work and then you were like, oh, well, I'll just take this number, and you didn't label it, and then you don't know what you're doing. So it's just to prevent anything like that from happening. Okay, so Avogadro's number is 6.022 times 10 to the 23rd equals 1 mole, right? So I'm going to set it up, and the number goes at the bottom this time because we want to cancel out the atoms. Atoms, krypton, we're going to get 1 mole of krypton at the top. Atoms, krypton cancel out, and then we get moles. So I made this number easy to divide. So 12.044 divided by 6.022 is actually just 2. And then you can think of the times 10 to the 23rd just canceling out. Okay, so we get 2 moles. So that one's easy. And then we are going from from moles of sodium to atoms, right? So our known here is the moles, our unknown is the atoms. So let's go ahead and start with our known. Sodium. And then we need to go to atoms. So we're going to set up here the opposite. So instead of the Avogadro's number going at the bottom, obviously we're starting off with 1 mole. 6.022 times 10 to the 23rd. And then moles cancel out. And then when we calculate this out, we get 1.54 times 10 to the 24th atoms of sodium. So now I kind of hinted to this earlier, but I mentioned to look at the masses here and how they were all different. All of these have 1 mole, right? Which means they all have Avogadro's number of atoms, right? All of these have the same number of atoms, every single one. Now they're all different masses. And that has to do with the fact that each one of these types of atoms, so each of these elements, has its certain mass associated with it. So think of how a dozen of donuts weighs differently than a dozen of bricks, right? Just, you can think of that, like just visualize it. You have 12 bricks, they're super heavy. Compared to 12 donuts, it's just like a light box, right? So that's the same reason that all of these elements have different masses. So it starts to kind of all make sense once you start thinking about it, like with real life things like donuts and bricks. So, and this actually is something called molar mass, which we're going to discuss on this next slide. So from now on, every time that I ask you for a molar mass, or I ask what's the molar mass, you need to look on the periodic table. So you should have a periodic table. Hopefully you can print one. If you can't print one, just maybe have one on your phone, like download it and just have it like out whenever you're working on chemistry problems so you can zoom in and look around. And you're going to look at the periodic table and you are going to look at the element and look at this number. This, we learned it as our mass number, right? But it's also our molar mass. So our atomic mass, our molar mass, same thing. This is our atomic number, right? That's different from our mass. Now, something else you should know is that 1 AMU is equal to the unit of molar mass. This is the unit for, and I like to summarize molar mass as MM, big M, big M. So this is the unit. So anytime you look at the periodic table, let's say we're looking at carbon, we see that the mass is 12.01. We can automatically assume that 12.01 is grams per mole. And we can actually use that as a conversion factor. So here's the unit equation, molar mass of carbon. We can also set it up as a conversion factor essentially. So either the 12 grams at the top or in the mole at the bottom, or the other way around, whatever we need to convert. So now that we know what formula mass is, right, we learned that at the beginning, and now that we know what molar mass is, I also just want to point out, again, just to make sure you understand, formula mass is also equal to the molar mass. So here we calculated the molar mass, sorry, the formula mass of caffeine earlier, but it is also the molar mass. So remember our mole map from earlier. We actually have another addition to it. Now we can go from moles to mass using the molar mass. But again, the mole is going to be at the center of everything, and you'll see once we put all of this together. So let's practice converting from moles to mass. So we're going to start off here. How many grams are there in 1.45 moles of Ne? So our known is our moles of Ne. Our unknown is grams, right? So you start by setting up your known. And you can abbreviate moles with MOL. That I allow, but not labeling at all. It's better if you just get into the habit of labeling everything like it in its entirety. So 1 mole of Ne, and then for the mass, I'm gonna go look at the periodic table. So I got the molar mass of neon from the periodic table, and I wrote it up here. Now, once we add this in, we can go ahead and cancel out the moles of neon, and then we can calculate it out. And then what we end up getting is 29.26 grams of neon. So actually, now that I look at it, we have to round this. So for molar masses, I don't take them into account for sig figs, because essentially they are set values that have been calculated already. So I'm just going to look at the sig figs in our original number, which was 3. And I'm going to go ahead and round this. So 29.3 grams of neon, right? And then I was a little proactive this time, and I wrote down the molar mass of potassium for the next problem here. So on this problem, it's asking us to convert essentially from mass. So this is our known, and we're going to moles. So we are starting over here and we're going that way. And again, like I said, I usually denote molar mass with big M, and then the symbol. So let's set this up. We are starting off with 75.7 grams K. And then the way that we're going to set it up is the grams is going to go at the bottom. And this is equal to 1 mole of K. And then this cancels out, so we just have to calculate it out. So then we end up getting 1.94 moles of K. So now this final example is showing you how to get from a mass of an element all the way to atoms. So essentially we are starting here. We are going to moles using the molar mass, and then for moles we are going to atoms using Avogadro's number. So let's go ahead and set that up. Our known is our mass, and then we also know our molar mass of copper, and then our unknown is our number of copper atoms. So I got the mass of copper, and I went ahead and set it up just to save us some time. So I took the mass from the periodic table, and then I put the grams at the bottom, they cancel out. We end up at moles, so now we're here, moles of copper. We still need to get to atoms, so we are going to use Avogadro's number. So 1 mole of copper, 6.022 times 10 to the 23rd atoms, Cu. And then that cancels out. All that's left is to calculate that number out. So you should end up getting 4.73, actually 4.74 if we're going to round to sig figs, times 10 to the 22nd atoms of copper.